Welcome to the replay of the presentations held during the DigiDemo final conference that took place at ESTA Belfort on June 14, 2023 in Belfort, France. Within the DigiDemo project, the partners created 20 demonstrators allowing improving students' understanding and capability to develop smart, connected products. The DigiDemo project got a co-funding from the Erasmus Plus program of the European Union. If you are interested in learning more about the project or the demonstrators that have been developed, please visit the project's website at the address www.digidemo-project.eu. This third presentation resumes the results produced by the DigiDemo partners. The session starts with a short introduction to the project by Esben Skov Laursen from UCN in Denmark. Then Thomas Röhr from ESTA Belfort in France presents the results of the literature review and the partner program's benchmarking. Followed by Horatiu Pilsaon from FH Vorarlberg in Austria, who describes the developed framework for demonstrators and their evaluation. The results end with Train the Trainer, a concept developed and introduced by Hvidsten from Fagskolen I Viken in Norway.
Esben, yours.
Thank you. Thank you, Thomas. First of all, thank you to Thomas and Esther for hosting this final event in the DigiDemo project, giving us this opportunity to share our project results. We look very much forward to this. I will give an introduction to the background of the project as a starting point for diving deeper into the project result and deliverables. And the starting point for this project have really been this trend transition with digitization and the green transition, which is normally called within the EU. The starting point in our case were the mechatronic or the IoT product, but having an idea that taking into account the sustainability issue. The reason this is essential is because companies in the future need on multiple levels to take this into account when they build new products and new services, both the digitalization and the environmental issues. So therefore, this is one of the main drivers for businesses in the future in order to stay competitive. In order for the companies to fulfill this, they need a workforce that are having the right skills and knowledge and are able to take on this task in practice. So in the DigiDemo project, we have tried to fulfill this need, taking into account the context and needs from practice, because developing digitized products requires collaboration across domains, which complicate matters. And this is only accelerated or further complicated by adding sustainability to this task. So seeing this from a teaching point of view, this becomes a very complex task. Just a task of introducing these matters in the lectures, but also there could be some structural or organizational things that complicate things further. So therefore, in the project, we have seen a need for support the planning and executing these interdisciplinary activities among our institutions. The way we have tried to address this issue in DigiDemo is by strengthening the cross-disciplinary capabilities and awareness on digitalization and sustainability among the students. And furthermore, we have had the aim of supporting our teachers in planning and executing these activities. More specific, we have developed 20 demonstrators in the project to be used in lectures, and as a framework for these lectures, we have a framework for these demonstrators. we have developed a guideline to support the teachers developing deep demonstrators. To make the project resolve sustainability, not in an environmental manner, but sustainable, meaning living on after this project. We have also had the aim of developing an online teaching course, so people outside this project also could gain from the project's result. But these are the results that we will dive into in a second with the help of my colleagues. The organizations in the project is UCN from Denmark, and ESTA, where we are today, and Fagskolen Vorarlberg from Austria, and Fagskolen in Viken from Norway, and UBB from Romania. The DigiDemo-Project is a strategic partnership project for higher education, and it's co-founded by the Erasmus+ program of the European Union. So when we as a partnership find this interesting, doesn't mean that we haven't been working with this beforehand, the project. We have to bear in mind this project was started almost 4 years ago, let's say 3.5 years ago at least. So it's not like we haven't been working with these issues, digitalization and sustainability before, but we all felt a need to dive deeper into this and also perhaps to combine these two elements more effectively, both let's say from a knowledge point of view, but also from a practical point of view when we're talking about our lectures and educational programs. So although we have worked with this before on different levels, we found it innovative and complementary to start this project and dig further into the matter. Before handing over the floor to my colleagues, where we'll dig deeper into the details of the project, I just want to share this slide with you, and I know it's a bit wordy slide, and that's actually meant to be a wordy slide. But we have to remember when we do these Erasmus+ projects, they're not just about the specific content which we have specified in the application. They go beyond that. So part of being in a Erasmus+ project, it's also about developing the individuals in the project as well as the organizations. And not just in a professional manner, but also it could be in cultural matters or language or relationship. So bear this in mind when you are in a Erasmus+ project. And I personally think that we have fulfilled this part very much in this project beyond the specific project result we have gained so far. Yes, thank you very much. So I'll leave the floor to Thomas.
Thank you very much, Esben, for this introduction to the DigiDemo-Project. From our side, was a real pleasure to cooperate with all the partners in this project, and also our students appreciated contributing to it. We've been responsible for the, let's say, state-of-the-art part at the beginning of the project, and that's the part I want to present here. So we are all, or most of us, are working at universities, or higher education institutions, sorry, in the engineering or already mechatronics domain. Mechatronics is one field where we have somehow intelligent products that already combine mechanics, electronics, control system, and so on. You can see on this slide here on the bottom right one of these definitions that we have found from 2016 about what's mechatronics and what are the the interfaces between the different elements. So we have the electronic systems, we have the mechanical systems, we have computers and control systems, and then we have these overlapping elements. And in the middle, where all these comes together, this is mechatronics. Mechatronics is a pedagogic domain that has developed towards a non-educational thematic. So it's not anymore mechanics plus electronics plus computer science plus control systems, but it's something integrated and has become a new field. So that was our starting point, because we are working in this mechatronic field. But if we speak about smart connected products today, mostly we think about IoT. So if we look on IoT, this is if we look on IoT, this is mainly linked to computer science studies. It's not in the engineering or the mechanical or electronic engineering departments, but in the computer science department. And if you look on publications about IoT, it's very often addressing the network aspects of this network of things, Internet of Things. It's addressing data mining, data handling applications, but it's very seldomly addressing the things, or these products. Or now the refrigerator or the whatever, the loudspeaker, whatever is connected. And this was so one of the two, or one of those difference between mechatronics and IoT is one is in engineering, second one is in the IoT, in the computer science section, and then the one is looking on products, function hardware, where the others are looking more in network activity, so where hardware elements are key. One of the differences that come out of the literature research is that mechatronic product has intelligence embedded in it, so that even if the connectivity is going down, these products can continue to work and to adapt to some situations. Where if you look on IoT things, that they absolutely need the connectivity. If not, they are not working in. And the intelligence is often in the cloud and not anymore in the product. We tried to build a similar image as the one we've seen for mechatronics for IoT, which has been quite difficult for two reasons. The first one is that we didn't find a lot of IoT studies. So IoT is part of computer sciences as one lecture, but really full IoT dedicated study programs, we only identified 4 in Europe, 2 in France, 1 in Spain, and 1 in the UK, if I remember well. And we tried to figure out, okay, what are the common elements in these study programs? And the result that we can see here in this circle for IoT. So we can see advanced computing, cloud computing, security, privacy. You can see that all this is more data handling than the final product, which is handled in these study programs. What is the link between both? So we know that the need for connectivity of products is rising, even for mechatronics products that have the intelligent embedded connectivity becomes more and more important. If it's just for new parameters for sending drawings in or production parameters for maintenance issues and so on. So connectivity is becoming more and more important. We have also elements that start to measure parameters of the system and then send them to some central systems for analysis, for predictive maintenance, for new services, and so on. So there is a real need to link finally mechatronic products with some kind of connectivity. And that's what we tried to figure out what that means. So we try to put on the one hand, on the right hand, we can see these different elements of the first mechatronics we've seen, and on the left hand are the topics that we've identified by analysis of these different study programs. And what we can see is that there are some that have a common interest. So those which are in the middle, the blue ones, dark and light blue, digital control systems, sensors, actuators, network integration, advanced computing and computer. So which are either linked or similar with just different names or interesting programs. So the idea is to say, okay, mechatronics already integrates mechanics, electronics, and all we've seen before. The question is, do we need to add some kind of connectivity to mechatronics to enhance the developers of future mechatronic products to be able to add connectivity to the product, to understand what's feasible with the data on the one hand, but also to add things to the IoT part so that they understand, okay, what's feasible on the thing side. So this was the idea. Now we started to look into study programs to see whether we can identify how far these IoT elements are already considered in mechatronics study programs. So mechatronics study programs are much more common in Europe than IoT programs. And we analyzed a total of 23 bachelor, 4 masters, and 4 other programs. So other programs are generally schools that don't have a bachelor master system and going for 4 years or from 9 countries, the 5 partner countries and 4 others. And the approach was a very pragmatic approach. We just took the program, extracted the names of the different lectures inside this program, and came up with a list of 740 individual unique lecture denominations. And what we've done then is that we classify them in what we call sub-competence groups. To give you an example, mathematics 1, mathematics 2, algebra, statistics, all this went into one subgroup called mathematics. So that at the end, from these 740, we had left 72 different, somehow standardized denominations of sub-competence groups. And these sub-competence groups have been regrouped in main competence groups, and they are going to 5 over groups. So what is the result of this? Like you see on this one here, we can see these different subgroups. Yeah, so you can see on the one side mathematics, for example, with 100%. So in 100% of the 23 mechatronics bachelor programs, some kind of mathematics was taught. That's what 100% means. If you look at electrical engineering, in 74% of these 23 lectures, electrical engineering has been taught in some kind of degree. It's not said that whether it's just one lecture or whether it's a focus subject in this mechatronics program. That's not said at this. We can find here these all the competences that are present in at least 30% of these 23. So in more or less 8 of at least 8 of these bachelor programs. Half of the 72 we identified at the beginning are present on the slide, and we can see that 15 of them which are in the middle blocks and in the IoT part up there, which are present here, which are really directly addressing mechatronics and or IoT topics. The rest is what we call general knowledge like physics, mathematics, and so on, or the rest like project management, like some kind of management lectures, and so on. But we can see that from these overlapping parts, IoT is already we presented in mechatronics programs, data processing, not really, only in one, in 34%, or something like 8 of these. So IoT skills could be improved in mechatronics programs, and that's somehow what we intended to do with DigiDemo demonstrators, to develop demonstrators that combine kind of mechatronics, kind of combination of mechanics, electronics, and so on with that connectivity. So where you can see information on the smartphone or steer the element with the smartphone. The last step we've done is we compared the existing study programs from the partners with these subgroups to build this benchmark we can see here. There are two elements considered. The first one is completeness of study program, so which is the x-axis. 100% means that all the different the different 36 subgroups that have been mentioned on the preceding slide are represented in the program. And 70%, as for ESTA, means it's only 70% of these topics, where the main competent or main subgroups that have been in this group represented in more than 70% of the programs have a weight of 1, and the others a weight of 0.5 to distinguish a little bit between. And the depth of teaching, the X, the Y, or the Y axis on the left side, that means that we asked each partner to evaluate whether the topic is taught in a weak, normal, or intensive manner. So if you have a focus on electric engineering, for example, then electric will be weighted with a 3. And if you have only some kind of basic education, then the weight would be more or less 1. And if it's not taught, then 0. So, and this gives the level on the left side. So we can see is that for FR Vorarlberg, who have a real mechatronics program, is on top with what considering the depth of the teaching and learning, but they don't have all the lectures that came out of this study program analysis. Not yet, perhaps. That's all from my side, from the state of the art. Was an interesting work with interesting insights. Thank you very much. I use the floor to Horatiu.
Okay. Thanks to my colleagues for this interesting first and second part of the presentation. Now, my job is to talk a little bit about the framework for the demonstrators, for the simple reason that our institution was in lead for this framework. So that's why this is my part to do it. You have to highlight it. Okay. This is what I want to talk about. I won't go into detail of the agenda of my talk because we're going to go into detail to every point. So skip that. I would like to talk a little bit about the motivation. So what was the motivation for doing this framework? Well, the motivation started with the following text, which was part of the proposal, the draft idea proposal from UCN, from you, Esben, or maybe one of your colleagues, or you too, which is, I am going to read it aloud. The primary objective project is to develop a number of demonstrators based on cases from industry, which can be used to develop new educational material, methods, or approaches aimed at improving the students' interdisciplinary capabilities. That was the first idea of the project, which crossed me, or which I came apart. And then the question was, okay, what is a demonstration? What should we do with this text? We have to do something in order to find out what a demonstrator is. I'm still used to switch, use the keyboard.
Yeah.
So, what is a demonstrator? And we had to think about that, and we came up with a few ideas. The first idea was, well, if we have a demonstrator, we have to define some characteristic this thing has. But the characteristic itself is not enough. So the next thing, the next thing we came up, we said, okay, we are from different institutions having different types of programs. Ah, thank you. That's great.
One, which was a wheel.
With a wheel.
With the wheel.
Thanks. Different institutions having focus on different, we call them chain or value chain steps in the product. So we have to consider some dimensions which where we can group the demonstrators into in order to make a reasonable demonstrator. The next would be, okay, a demonstrator has to consist of something, and then we discussed about elements which a demonstrator must have at least, or minimum, or even more than that. And then finally we found out, okay, that's great, but we need something. If someone wants to find out if this or the other demonstrator fits his or her need for a class, then it should be easy to find this out by just reading a few keywords, and that was your idea, Thomas. And we came out with the key properties of the demonstrator, which makes it easy for anybody to understand, okay, this is something for me or it's nothing for me, because I can't read it. So that returns me to the characteristics of a demonstrator, and we have 5 of them. I think they are more or less obvious, so I won't go into detail. It should improve teaching. That was the first idea. That's what we are doing and what our colleagues are doing. We are teaching future engineers, and we want to improve this teaching, and that's what a demonstrator must do. The next is sustainability awareness. When we came up with the idea of this project and then we added the sustainability, I said, we can't do that. You can't chase 2 rabbits. Doesn't make sense. That was wrong. I have to admit that's a good issue to add the sustainability awareness almost in every project we're doing in engineering, because we need this awareness in the future more than in the past, of course. We need this in order to do reasonable things as engineers. So this improved sustainability awareness was a part of our characteristics of the demonstrators. The next thing was the idea that if someone sets up a demonstrator, someone else should be able to replicate it. And this is the third characteristic, that we supply all the data needed so the other person can replicate the demonstrator. As stated in the individual text, we should take care that it follows industry needs. That's what we want to do. We want to have engineers that know what industry needs. And in order to know what industry needs, we have to comply with these needs of the industry. And last but not least, it should be interdisciplinary, because this is the way engineering looks like nowadays. And these were the characteristics we set up. And the structure of our framework, if you take a look at this here, is actually more or less the agenda. So what the framework does, it's a document which defines how to describe a demonstrator by stating how to describe characteristics, key properties, dimension, and some additional information like educational, organizational, and description of the technology. And if we could go back 2 slides, I won't do that. This is exactly the agenda, because what I'm going to do is to follow the document and try to explain what was the idea behind setting up the document in the manner in which we did it. So I've taken this here out. because I want you not to read the text which is behind it. So what we set up is, let's take a look if it works. Should work. Well, this is the text, but I don't want you to read the text. So the idea is the following. We said, if we describe these characteristics, it shouldn't only be, yes, we're doing that, or not, we're doing it, not doing that, but we want you to formulate why this is a teaching improvement and why you can improve sustainability awareness of a demonstrator with a demonstrator for the students. And in order to understand what you're doing, this is something we like to help the people setting up demonstrators to understand that they are doing the right thing. And now we can take a look at the content, an example context, which shows us does not. It takes some time to do that, yes. How we did it, so we formulated a text stating how this is improved. For example, the sustainability is not addressed explicitly in the demonstrator itself, but it is in the educational setting, because this was something in this case that was important for us for this demonstrator. So this is the one thing, the characteristic which should be formulated in this manner. The next are the so-called key properties, and the key properties that should be simple. Simple means we only need these elements. The first is the level of the education in terms of EQF, 5 to 7 usually in our case, year of study. The objective of this demonstrator, the domain, should it be mechatronics or IoT, the workload, hours, credits, whatever, and some keywords in order to make it easy to find it. And you have an example over here stating one example with these few words. So in this case, we don't need a text. We only want a few keywords, a few figures, a few numbers in order to find out what it's all. So this is how the key properties look like, which enables someone to easily find out, is this demonstrator something that is interesting for me or not? The next issue are the so-called dimensions for classification, and the dimensions for classification come out of the idea that we have different programs which follow different needs, or we have different issues where we can classify the demonstrations. You find a lot of keywords over here. I won't go into the keywords right now. I will do it in an example, which we take a look at now. So let's take a look at the value chain. The value chain is to follow the value chain actually of a product, starting with development and sales and after sales and end of life. As you see, we try to make it easy for the people. They have just to pick which part of the value chain it is. And this goes through the entire thing. So we have chain of technology, which includes electronics, mechanics, sensors, stuff like that. We have sustainability. Then we have issues like physicality. It could be a simulation, but I think in the cases of the 20 demonstrators, we only have physical setups. Easy to understand, students prefer something that they can hold in their hands in order to learn. That's why in German it's called begreifen, right? The degree of student freedom means, is it something that the students do autonomous? Are they coach guided or demonstrated? It could be something that you only show to the students. Then transportability is an important issue, of course. Is it fixed, transportable, or portable? The difference between the last two is portable is something that you can take in your bag. Transportable will be more than that. Then we have the costs and the workload. And one thing to keep in mind, this workload is not referring to the workload of the students. That was in the key properties, but to the workload of the teacher in order to implement and bring it to operation. And then some other things like size, weight, and so on and so on. So these are dimensions which gives the possibility to classify demonstrators in order to find out, is this demonstrator suited for me? So that would be actually a two-steps approach for someone interested in. First step would be take a look at the key properties, and then if it is suited, take a look at the classification. And then we have, of course, some additional information which is important for the teacher. The additional information is that for this educational information means where is this demonstrator or in which study program has this demonstrator been used? In which course has it been used? The course description. How has it been integrated into the course? And how is the sustainability awareness incorporated in the demonstrator and the course to help someone to reuse the demonstrator? The next type of information, if it shows up, is something like organizational information, which means typical organizational issues like project duration. Is it only a few hours, is it a few days, and so on and so forth. The team size, if it is a teamwork, and usually it is a teamwork because we want this interdisciplinary approach, and teamwork easier is that. And type of activities that you need before and afterwards. And the last is a brief description, more or less brief description of the technology and the setup. Brief means a list of files. Yeah, it could be you see some CAD drawings, assembly info, and so on and so forth for the mechanical parts. It could be schematics, parts list, layout data, and so on for the electronics. You would have software diagrams, you would have code for the software. You have a manual if it's available. You need a list of documents if you supply several documents like the one before. And of course, if needed and if possible, some background information or rationale on why you did it, how you did it, and so on and so forth, making things easier for the teacher who intends to use that to really do it. So this is basically what the framework consists of. What we also did is an evaluation of the framework. This means we did the evaluation in two steps. The first step was to evaluate the framework itself. And the second step was to evaluate the framework through the demonstrators, because by making and evaluating the demonstrators, we were able to evaluate the framework and to close the cycle, the closed loop cycle, in order to improve the framework even further. And that was done in two manners. One was done in a peer review by the members of the project teams, my colleagues and me. And the other one was an evaluation done by the students as a result of using the demonstrator in teaching, because that's the main reason why we did it. So what's the outcome? The outcome was the framework at the beginning. It was a good starting point. Was a good starting point for my colleagues to set up the first demonstrators and the other ones too, of course. During the project, we had only a few changes in the framework, and I'm glad we had that. So if we had no changes, that would have been a bad sign. Means it wouldn't have been a living document. It would have been a document which we improved. If we had a lot of changes, that would have mean we didn't do a good job at the beginning. But if we had only a few changes, means we did a rather good job. And it was a living document, and that was our goal. And the third thing, da kommen jetzt. We have a set of 20 demonstrators which have similarly structured descriptions, because that's what the framework gives us, a description structure for a demonstrator. So we are able somehow to take a look at 20 demonstrators and say, this one would suit my need and this one won't, or maybe none of them, or maybe all of them, who knows. That was my part in the presentation today, and I'm glad to hand over to Tommy. Tommy.
Good afternoon. Nice to be here. Thank you for a nice meeting in Belfort. It's a bit hot, but it's weather is nice, sun is shining, so we're happy. And also thank you for a nice journey the last years together on the DigiDemo project. Our part of this, our main responsibility has been the training system, and I'll try to tell you a bit about that. The point of
It's the mouse.
yeah, okay. The task was to make the e-learning system or content of e-learning that you can publish on the website. And the first approach was to try to define some learning outcomes that we want to achieve through that e-learning system. And those learning outcomes is obviously about people going through the e-learning should know about the demonstrator framework and the pedagogical application of it in the context of interdisciplinary teaching and learning. And also about the demonstrators itself and how you can use this to create good interdisciplinary learning in your teaching. Skills to apply this both the demonstrators and the framework. And at the end, the competence part of this, the trainee is responsible for the successful application of the DigiDemo framework and the demonstrators for enhancing the learning outcome in these settings, which is relevant for the project. We made a specification to make one e-learning section consisting of 2 video-based learning elements, covering both OE1 and O2, which has been presented earlier. And of course, we used a demonstrator as a case. So we are following the what I like to call the first principles model of Merrill, which is like problem-based learning, basically case-based learning, and they're trying to design the e-learning system around those principles. And recommend his book if anyone is interested. Or it's a lot of resources on the internet as well, which is covering the same theme. And for each section, we have for each of the 2 sections, we have made a paper, a video manuscript, and we have made the video, of course. And it's also a test for testing the learning outcome of the people that want to see if they have actually grasped the content of the e-learning. The case which chose to be the focal case is a demonstrator built for measuring snow depths on a cabin roof. We'll come back to that. And we will present that demonstrator and the context it's used in, and also with how it is used with the students. And then in the second video, we present the framework, which Horatiu just described for us, and try to convey the different sections of this. So this is the aim here, is of course teachers visiting our websites to try to learn more about the work we have done and maybe apply it in their own teaching. So without further away there, I'll try to show you the 2 videos. It's like 2 times 6-7 minutes, and yes, I'll do my best and even the right button, I hope.
Welcome to DigiDemo and the Internet of Things, the first in a series of 2 educational e-learning elements which constitutes a framework for learning activities in the contemporary industrial world. But first, DigiDemo is a project funded by the EU through the Erasmus Plus program. Participants in the international group are Fagskolen Vorarlberg from Austria, ESTA Belfort, based in France, the Central University UBB Röhr in Romania, and Viken Higher Vocational College, based in Norway. The lead applicant and coordinator of the project is University College of Northern Denmark. IoT is short for Internet of Things, and is a concept that all the things around us can be connected to the internet. This enables us to remotely control the things and collect data in a way that previously was impossible. With IoT, we can enhance products, make work and business processes more efficient, reduce costs, and create new digital services. Thus, our products and services increase in quality and the businesses become more profitable. IoT is a central part of Industry 4.0 and boosts the trend towards automation and data exchange in manufacturing. It is also an important tool for sustainability in products and processes. In this video, we present tools for learning IoT and how it can be implemented in products and creating new services. Through IoT, modern manufacturing is highly interconnected, monitored, and autonomous. We collect data to predict maintenance needs and learn about the process's pros and cons. In this way, we can improve our facilities. Our products become smarter, enabling us to increase quality and launch new services, such as smart homes. The introduction of IoT in products and processes demands new skills and a holistic approach to development requiring interdisciplinary competence. The DigiDemo-Project has developed 20 demonstrators to be used in practical and experiential learning activities in higher education that aim to teach IoT. This first video will present one of the demonstrators and how it is used by the students to acquire IoT knowledge. The second video will present the generic demonstrator framework and how it is applied on the demonstrator presented here. The case in question for our demonstrator addresses a problem with dangerous amounts of snow amassing on the roof of Norway's holiday homes. Many families have cottages in the mountains for relaxation and as a point of departure for skiing in the winter. Most of the time, the buildings are remote, and the snow may amass to dangerously high levels. The demonstrator is based on a product and integrated service developed by a small startup company named Hvidsten. The question was, how can we monitor the snow depth on the roofs and warn the owners of imminent dangers due to high snow loads that may cause structural damages to the building? To answer the question, we face some challenges. Many of the cabins do not have electricity, so how can we overcome that? They often do not have Wi-Fi. Can GSM communication be a solution? Snow is not just snow. There's a reason for the Inuits' more than 50 different terms describing snow. How can we make good measurements under all conditions? Moreover, we must also consider various aspects associated to sustainability. For example, how to maintain, repair, reuse, or eventually how to recycle the product.
From my point of view, there are three important factors in a good lab demonstrator that supports the students' learning. First, you must have the technical content the curriculum require. Secondly, the demonstrator itself must have a real-world relevance, and it must be a product that the students can relate to. And third, it must have a challenge the students feel they can solve. In the task on this demonstrator, the students have done the programming and the setup of the services that support the product.
I feel that I've learned a lot from the demonstrator. The most important thing is that we have free hands to analyze, plan, and organize how to solve the task.
It's also very good to know that the task we worked on makes sense, that someone can actually use the final product.
This image shows the architecture of the solution for the snow depth measurement demonstrator. a laser distance sensor from Garmin named LiDAR Lite version 3 is used to measure the snow depth. The LiDAR will provide valid measurements from different kinds of snow qualities. The sensor is connected to an Arduino MKR 1400 GSM controller module. The microcontroller will gather sensor data and distribute the measured values using the MQTT protocol. The program running on the microcontroller will be shared and documented to enable students to make their own adjustments and to understand how it works. GPRS will be used on the microcontroller to provide connectivity. The MQTT protocol defines the message structure and format, and the data will be carried by the TCP/IP protocol. In the cloud layer, 2 different software packages will be used. The Mosquito software will provide an MQTT broker service to manage the data messages and distribution, and Node-RED will receive information, process it, and display the information to the user in the application layer. The image shows the demonstrator with the LiDAR sensor and Arduino controller with GSM communication. Note the cable to the external antenna and the connected LiPo battery. The twin transition of sustainability and digitalization are addressed in the demonstrator. Firstly, the demonstrator will contribute to quality education. Secondly, affordable and clean energy is addressed through software-controlled energy management, ensuring minimal consumption of energy. This is also supplemented by the application of a solar panel for battery charging. Thirdly, the demonstrator will contribute to building competence in IoT, supporting sustainable development in industry, innovation, and infrastructure. For more demonstrators, access the DigiDemo homepage, www.digidemo-project.eu. This concludes the introduction to the DigiDemo demonstrator. After you have finished this video, take some time to reflect upon and suggest answers to these questions. 1. How can you incorporate interdisciplinary learning in your IoT training? 2. Are business cases a natural part of your IoT curriculum? And 3. Is experiential learning through practical demonstrators relevant in your IoT, product design, and manufacturing training programs? The next video in this series will be about the framework of the DigiDemo series of pedagogical demonstrators for IoT training.
Okay, that was the first movie. You will see that there's a arch which is similar in both movies, and that the idea behind that is that you can use them independent of each other. That's also possible. That could be useful as well if you are studying things carefully. But enjoy the second one. To start it.
Welcome to DigiDemo and the Internet of Things, second in a series of 2 educational e-learning elements which constitutes a framework for learning activities in the contemporary industrial world. DigiDemo is a project funded by EU through the Erasmus Plus programme. Participants in the international group are Fagskolen Vorarlberg from Austria, ESTA Belfort based in France, the Central University UBB Rishita in Romania, and Viken Higher Vocational College based in Norway. The lead applicant and coordinator of the project is University College of Northern Denmark. IoT is short for Internet of Things and is about all the things around us that can be connected to the internet. This enables us to remotely control the things and collect data in ways that previously was impossible. With IoT, we can enhance products, make work and businesses' processes more efficient, reduce costs and create new digital services. Thus, our products and services increase in quality and the businesses become more profitable. IoT is a central part of Industry 4.0 and boosts the trend towards automation and data exchange in manufacturing. It is also an important tool for sustainability in products and processes. In this video, we present a framework for creating tools for learning IoT and how it can be implemented in products and creating new services. Through IoT, modern manufacturing is highly interconnected, monitored and autonomous. The DigiDemo-Project aims to create tools for interdisciplinary learning of the IoT technologies in an application setting. The first video presents one of the 20 demonstrators developed by the project and how it is used by the students to acquire IoT knowledge. The second video will present a generic demonstrator framework. The DigiDemo framework is a document guiding the description of the demonstrators. Following the documentation for a demonstrator developed according to the framework, it should be possible to build a demonstrator and understand the context it is meant to be used in. In brief, these are educational setups to be used in academic education of mechanical and electrical engineers in order to improve the students' skills in digitalizing products. The target audience of the documents are teachers using demonstrators in their educational environment or developing new ones. The framework document is freely available at the DigiDemo website. The first part of the document gives a description characterizing a demonstrator built according to the framework. The following characteristics apply for the demonstrators. 1. It shall improve teaching. 2. It shall improve sustainability awareness. 3. It shall be replicable. 4. It shall follow industry needs. And 5. It shall be interdisciplinary. 1. The demonstrator shall improve teaching. The rationale of a demonstrator is to strengthen the cross-disciplinary capabilities of students. By using the demonstrator in one or more courses, the learning outcome with respect to digitalization shall be improved. 2. The demonstrator shall improve sustainability awareness. By using the demonstrators, students shall be aware of sustainability issues and get used to include this aspect into design of every system from the very beginning. Sustainability is mainly meant as a sparing use of resources, both raw materials and energy, and good recycling properties. 3. The demonstrator shall be replicable. Any academic institution shall be able to implement its own demonstrator by using the data supplied by the creator of the demonstrator. This shall be feasible with as low as possible effort, both workload and materials. Hence, the demonstrator material will be open source. 4. The demonstrator shall follow industry needs. One of the main goals for using a demonstrator is to ensure that industry gets highly skilled engineers, able to promote digitalization of products. To ensure this purpose, a demonstrator shall be based on an explicit use case from industry, preferably of an SME, small and medium-sized enterprise, since these companies have higher challenges in incorporating digital elements into their products. In the description of this characteristic, the concrete industrial example shall be given. 5. The demonstrator shall be interdisciplinary. Interdisciplinarity is a must in today's product design. Hence, a demonstrator shall improve students' interdisciplinary skills. To address this issue, several elements of the chain of technology dimension shall be covered. In the next part of the document, the key properties of a demonstrator is specified. These are EQF levels for the intended education, year of study, objectives as learning outcomes, the technical domain for the education, and the workload in ECTS for the relevant subject. Further on, the document states classification dimension for the demonstrator. This includes which parts of the value chain the demonstrator is covering, the chain of technology, sustainability justification, the physicality of the demonstrator, the degree of student freedom, the transportability of the demonstrator, the cost and the workload to build it, the size, the weight, and any special request for the product demonstrator. The final part of the document contains an example of demonstrator documented according to the framework. This concludes the introduction to the DigiDemo framework. After you have finished this video, take some time to reflect upon and suggest answers to these questions. 1. According to your experience, are the stated characteristics for the demonstrator sufficient to improve IoT learning? 2. Is the documentation framework suitable for building and implementing demonstrators in your teaching? 3. Do you think the application of one or more demonstrators can improve interdisciplinary learning in your IoT training? The first video in this series shows an example of one demonstrator built according to the DigiDemo framework for pedagogical demonstrators intended for IoT training. Please visit the DigiDemo website to download this framework and documentation for the 20 demonstrators developed by the project. Thank you for watching.
Thank you, Tommy, for this presentation of the training concept. Training concept and these two videos that are really representing what we've done and our intention. So I think it's a very good basis for teachers to learn about the ideas of the DigiDemo-Project. Before we start the discussion, so here we tried to put on the main important key information on this final slide. So we have as main project outcomes these the result that we see a certain need to integrate IoT elements into mechatronics studies. We have the framework we've just discovered in the video. We have these 20 demonstrators that are working, that have been used in classes, that have been evaluated by students, and that will be used in the future by the partners and perhaps others when they download these demonstrators that are all available on the website for them. And we have the training concept that each is covered. But also some kind of, let's say, back view on the project. We have hit by COVID-19. Our first transnational meeting that was planned to be in Aalborg never took place physically, so we had to transpose it into an online transnational meeting. We had budget restrictions, we had travel restrictions, we had teaching restrictions. So the project had faced several challenges that have not been planned at the beginning. But I think we all managed to overcome these challenges, to bring the project to good, and we've done what we planned to do, and that's a very good result. We had a very good partnership, very good relationship between the different members of the DigiDemo team, and the real wish to continue cooperation between the institutions in further projects, exchange, teacher exchanges, and so on. It was also an opportunity, I think, for all the partners to discover how the other partners worked, what are their equipment and facilities, which are quite different between the different partners. And this was a really good and interesting experience.
Thank you very much for your interest in the DigiDemo project that has been realized by UCN in Denmark, Fagskolen I Viken in Norway, FH Vorarlberg in Austria, ESTA Belfort in France, and UBB Resita in Romania between September 2020 and August 2023. The project got a co-funding from the Erasmus Plus program of the European Union.